Hello, we are into the third case study, which is using compliant mechanisms to measure forces. So, all you need for that is a way of measuring displacement that you can do in many ways, especially at the micron scale where the forces are small. In this case, we are talking about micronewton force sensor made using compliant mechanisms. So, this work has led to what is called what we call a micron. This is a micronewton force sensor. It can also go down to smaller forces than that. It looks like this. Compliant mechanism is hidden inside little one, but that is a crucial element here. This was developed by Santosh Bhargav as part of his PhD thesis, who has now a company, and a number of students, in particular Ashwin Maheshwari and Harshal Gugale and Gautam Baichapu did a lot in calibrating it, and a few other students also contributed to this work. So, when you think about measuring small forces, there are a lot of techniques now. In fact, the smaller the force, the more the techniques are. So, starting from micronewton, these are all Newton, this is 10 power minus 6 newtons, all the way to 10 power minus 14 newtons, like 10 femtonewtons. There are a number of techniques, they are all acronyms. If you look at this paper that is cited here, you would know what these are. This MEA is microaspiration, AFM is atomic force microscope, OS is optical stretching, and so forth. These are the twisting cytometry, magneto twisting cytometry that Crick had pioneered, all of these, and look at cell contraction, protein folding, molecular motors, all of those biological things have very small forces. There are a number of techniques for doing this. If you look at the micro actuators, this is measuring forces, we are talking about actuators. We have plotted now maximum force and minimum displacement that actuator is capable of doing. Again, there are lot of different actuators. This is a paper by Mike Ashby's group 10 years ago or more than that. So, they have lot of actuators they have put here. So, we have actuators, we have force sensors. So, is that enough for us to work with biological cells where the things are very small? But then it turns out that there is plenty of room in between. So, when you look at either forces or displacement, whatever that is available out there for you to take, but there is a gap at the mesoscale. There is micronewton to millinewton range, if we call that as the mesoscale. It is hard to find useful sensors commercially available. And then we also have the problem with stiffness. Some other sensors, even though they are able to measure, they could damage the specimen. As we already discussed in the last case study, that cell stiffness can be as small as 1 millinewton per meter. So, such a small stiffness, unless your sensor also matches that, it will be a problem to handle biological cells. So, there is plenty of room in between the micro and the macro size. So, in terms of what is there, many of these sensors cannot work in aqueous medium. There are a few, but they do not work in a aqueous medium, that is a water medium in which cells are happy and alive. So, some of them are listed here, some of the selected force sensors from the literature. The resolution we talked about in the context of case study 1 with accelerometers. Similarly, what is the smallest change in force that you can detect? Here is one that detects about 50 or I would say 5 micronewtons, 10 power minus 5 newtons or 5 micronewtons. There are some which can measure 0.01 micronewtons also, right. So, there are things, this actually in micronewtons is actually much smaller. This is 15 10 power minus 5 micronewtons, very small in this particular case what they have made vision based sensing. There are others in terms of micronewtons, some are 2, this is our own work, some are 20, 100, 250 and so forth. Okay, there is varying capability. So, many of them are kind of research based force sensors, they are not commercially available. Commercially available ones, there are a few. This is from Femto Tools. There is a very tiny probe here, and this all MEMS chip measures capacitance change when there is force and there is displacement of the probe, that changes the capacitance, and there is electronics. You have to put this. It also works in water, but you have to put an inclined angle, and it is very delicate. You could just break and lose hundreds of euros on this. So, there are some that can measure. There are others that are capable of measuring tens of micronewtons. There are very few in the commercial world also. So, with the micronewton force sensor that I wanted to work, we had set some goals for ourselves. One is that it should be inexpensive. It should not be that probe anyway is going to be delicate if it has stiffness that matches stiffness of the cell, but when it breaks we should not be losing a lot of money. So, we wanted to make it very inexpensive, and the idea was to use mechanical amplifier, which is our compliant mechanism. It is vision based because we do not want to use any other sensing technique or transduction technique, because anything else you bring in, whether it is electrical, magnetic, thermal, all of them are going to interfere with the thing. And one confidence that we have is that we can design the stiffness the way we want. So, whatever range we want, and accepting a digital microscope to measure the displacement or the output or amplified displacement, all others are simple enough parts to be made in a normal workshop. It should also be easily usable. These are the things that we set out as requirements from the end user viewpoint. So, our compliant mechanism, as you see, is quite simple. So, all we have is one DaCM. You can see the displacement over here is small, it is larger over here. It had a stiffness of 2.6 Newton per meter at this tip. That is, if you apply 2.6 newtons, you will get a meter displacement. That is a lot. Of course, this will break by the time. So, instead what we could do is 2.6 micronewtons, and that would lead to 1 micron display. That is what we want. So, micronewton force, micron displacement. So, stiffness has to be of that range. Micrometer displacement is amenable for measuring using visual techniques, just optical microscopy. You do not need to go beyond that. So, we can go for an off the shelf digital microscope and measure this very small displacement. So, that was the principle. Look at the size of it, it is 28 millimeters. So, this length from here to here is 28 millimeters, and it is not that small, in fact does not need to be. So, even these widths here, if you see the narrowest beam which is over here, that one is 0.7 millimeters. So, 700 microns. You do not need to go for microfabrication also to make this. I will tell you how we had done. So, we can design these things to have the stiffness that we want, so that small forces applied over here will cause measurable displacements using a digital microscope. So, here are some of the things that we had already seen. When you apply force here, how it goes. We also had seen this accelerometer where the DaCM is there. So, there are enough of these at our disposal, and we also wanted to make it easy to use. So, the delicate element is this: even if it breaks, we take care to make it strong enough, but can still break if the handling is not right, because supposed to move in the plane, if somebody yanks it out of the plane, it is going to break. So, we want to make it more like a cartridge here. So, this cartridge like thing can be slid into this digital microscope. This is a digital microscope, some camera that is there. You can put a USB connection to your laptop. So, that will measure the output displacement. So, if it breaks, we can put another one. So, that was it was done. Basically, a camera plus a compliant mechanism and some computing lead to a force sensor. Okay, this can be done in a number of ways, and of course, some image processing where that computing will be there. So, to design this we had used the spring lever model and put in our requirements as upper and lower bounds on the input force, that is what we want to measure. So, we know what to put here, and what is the actuator stiffness. So, that is in this particular case we are going to move, that is not so much, I mean that does not matter here. How much displacement of the input we do not care, but we have to care in terms of the object's stiffness here, because the input for this comes from the cell. Okay. So, over here what we mean is actually stiffness of the cell. If we know that for this force how much displacement we can expect, we can put that in, because we have approximate idea of what the cell stiffness is. At the output there is no force in this case, so the force is 0. So, put 0 0 on both sides, it only moves, and external stiffness. So, this also will not be there, 0 0, but we are interested in output displacement. So, we can say we are happy from 1 micron to let us say 3 microns or something like that. We can specify this and then generate the feasible space for it, the 3 dimensions in KCI, KCO and N, that is spring lever model parameters, and then look at various compliant mechanisms that are there. Input, in this case we put the input force 0.5 to 2 micronewtons, that is what we expect the cell to experience. Output displacement half a micron to 2 microns is what we want, minimum half a micron should be there. That with some image processing techniques you can figure out in optical microscopy itself. Input displacement we put 0.1 to 1 micron, that is in view of the input force. If I put 2 micronewtons and 1 micrometer as the input displacement, I am ensuring that the stiffness of the cell where we are getting this force from when we are squeezing a cell or cell exerting a force, we want it to be in the range of 1 Newton per meter or 1 micronewton per micrometer. So, you can see that some of them were lying inside, some of them are outside. This is the feasible map, and you can see that in this particular case we are plotting N versus KCI, not KCO, because that does not make sense. There is no output force, there is no output spring here, it just needs to move, it is more like an indicator mechanism. So, a number of mechanisms were considered, and using this technique we are able to choose one. So, like this is a growing database, we have lots and lots of these grippers in our database. So, we also use this non-dimensional analysis to see how we can resize them as we need. We have discussed this at length in this course in the earlier lectures, and how we drew for different slenderness ratios and decide the size of it, which also we went over in the last lecture. So, to see what either the overall length, this S slenderness ratio is L by D. If D and B are fixed by the manufacturing technique, E is fixed by the material that you have chosen, and of course, F is the minimum force you want to measure. Based on this map S value and eta, we can see what displacement, we know how much output displacement we can we want, we can actually decide this size, how much large we need to make. Okay. So, just to see that compliant mechanisms before we go to this micronewton force sensor, you can see a mechanism such as this. We had seen a real device, when apply force here up and this thing here moves like a pointer. So, in olden days people used to use things like that to measure pressure and so forth. Here we use this to measure soil moisture level. In all mechanical thing there is a little canister where you can put moist soil, and there is a wick like thing, and it is filled with super absorbent polymer which absorb the moisture from the surrounding soil, and it swells. That swelling is what is going to push here, the same mechanism we saw, and it moves this pointer. So, the mechanism is shown here, the solid model indicator mechanism, and just moisture swelling, which is a very little force. It expands by a factor of 3, that is 300%, but its force will be very limited. If you put your finger after filling the superabsorbent polymer there, it will not even move much because your force is enormous. But we have to design a compliant mechanism which has stiffness low enough that an absorbent polymer can push this and move this pointer, as you will see. Okay. So, this was embodiment design and it was all done, and here is where the pointer is going to move. The pointer is over here now, and when there is more moisture or less moisture, it would move. So, this video shows you this, watch this pointer here. Of course, this takes about 30 minutes. So, it is a speeded up movie. So, you can see this pointer actually moving from there to here. There is moist soil kept in this superabsorbent polymer thing. So, it actually moves all the way down. So, it is possible to do design compliant mechanism that can take very small forces and give you the displacement you want. So, the design of this micronewton force sensor described in these two in this paper, mechanics based design, where we have only static forces are considered. This is not dynamic force. The femto tool sensor can measure over a wide bandwidth, over frequencies if force is changing, but this one is more under static conditions. About 100 hertz is what we can reliably measure using this sensor, and fabrication is all normal workshop. You can see the workshop things here, and testing using biaxial modulus machine, so that we can measure the properties of the material that we have. Here is a mold made using aluminum or spring steel, and PDMS is the material used, which has a Young's modulus that is quite low, over 300 kilopascals. So, with that one we are able to make this one. Since a mold we can make as many as one needs. So, this is the one that is the mold for it, and you can again see the size is 25 millimeters, is quite large. The 28 is what we had seen, and you can make these things. And as I said, this like works more like a cartridge, where the middle one is the one, if it breaks you can replace. There is a little holder to hold a glass probe, glass needle or pipette as it is called, to attach to this. That is one is going to fix and probe the cell to apply force. So, that now we see this probe holder, to that you will attach a pipette. This is all with aluminums. It is quite big. Digital microscope will be about an inch in diameter and 4 or 5 inches in length. So, it is a bulky device, but can measure very small forces. Image processing to see that edge of that output thing, how it moves, that needs to be captured and analyzed for the displacement. And this is the user interface for it, where it will show the force as a function of time. It is a real time dynamic measurement. And this was calibration, that was quite a task here. So, it is whenever we use a compliant mechanism in application, we should remember there will be lot more details. That is what all these case studies will emphasize to you. It is not enough just to design some that has a topology or shape or size and some stiffness. Beyond that you have to worry about a lot of things. In this particular case study, the challenge was actually in calibration. We want to measure micronewtons, but we need to have a sensor that can measure micronewtons and then say that our sensed value is correct. Here that was a big challenge, because there was no other force sensor. What we ended up doing was go to a very sensitive balance and put the probe there, whatever this shows, and we compare with what we get. That is what we have to do. If you think about micronewtons, even if you are using like a weight in order to calibrate, that will change from place to place, because millionth of accelerated gravity changes will be there when you go from one building to another building, or even in the same building, top floor to bottom floor, and different geographical locations. So, calibration here is quite tricky for this micronewton force sensors. So, here we had some model and theoretical model with finite element analysis and the experimental result measured, and they are linear, they are not exactly coincident, but that can give you, and stiffness as I had said earlier is 2.6 micronewtons per micrometers, and from the experiment we were able to see about 2 micronewtons per micrometer, reasonably close. This is theoretical, this is experimental. And to use the sensor, that is also quite a task. We have this sometimes you want to go straight up like this, sometimes inclined angle, depends on what you are trying to do. So, you have to struggle with that mounting as well. And the compliant mechanism is a planar device here. It has to be enclosed in some between two layers, so that it does not go out of plane, because that also can change output displacement. So, that was also another thing that was taken into account in packaging this sensor. So, initially we took some zebrafish embryos and egg yolks. So, the student was very enthusiastic, whatever flexible material or soft material he found, he started testing that. So, when the egg yolk if you take, it has a force of about 150 micronewtons, this is 150 micronewtons, and the zebrafish embryo when you are pressing is more like indentation, you can say it went up to 100 micronewtons. Normal cells will be much smaller than that, the force that you apply on them is very small to deform them. Okay. These are embryos and egg yolks. And other thing was this feather. In the feather there are secondary feathers. If you touch them closing your eyes, you do not feel that. Micronewton force is something that we cannot feel with our fingertips. So, even if somebody puts this feather in your hand when you are closing your eyes, you can tell when the feather is touching you, touching your fingers or not. So, we are able to measure that. It was about 10 to 15 micronewtons when you push that, and I think there is a little video that shows that. So, 1 minute, we had seen this earlier, but we can observe it from the viewpoint of how this looks now. So, just to show that there is nothing, there is a digital microscope, here is where compliant mechanism is, and then the probe that is attached there, micropipette, there is really nothing, that is all. And this microscope looks at, a digital microscope looks at the displacement of the output point, and it is there. These are the things you do not feel with your finger, but if you put it with this sensor, we can actually see it, the output displacement happening and correlated to the force there. So, when you are pressing the probe and this zoomed in view of the feathers, you can actually see this moving ever so slightly and the value of the displacement changing over here. Okay. And we also did with carbon fibers and pollens and so forth. So, here it is carbon fiber tip, and that is what you see, the tip here. Pollen, it is very small, when you probe it, what forces you measure. It is moving ever so slightly, and you can see the value of that 3 micronewtons and so forth. And you can see there is a noise here, as we talked about, there will be noise, but whenever there is a big jump, we can see that now we pressed. Okay. And this is also used by people in IASC because they could not get any other force sensor commercially that works for this application. This was one of my colleagues, Professor Pratap's student, Dr. Rizwana Parveen now, she is in Singapore I guess now. They were looking at this haltere that exists in soldier fly. This is a modified wing which this insect uses like a gyroscope to know the angular rate here, and they wanted to know the stiffness of this haltere. So, this insect, soldier fly is like any other small insects, and there is this haltere in bright red color, and they wanted to know the torsional stiffness of this. So, they wanted to measure the stiffness. So, they have to take the soldier fly, probe it, push it here, measure the force, know the displacement. In this sensor, micronewton force sensor, we not only measure the force, but displacement is also available to you. We are measuring the output displacement. From the output displacement, we are calculating the input force. in the same process we also know the input displacement. So, we can actually give the bulk stiffness. So, the stiffness, how much force is applied, how much displacement we can get, and torsional stiffness of this beam, that is also compliant in a way. This is a nice technique that they are exploring to make a gyroscope. So, for them to understand this sensor was useful. So, I will play this movie to see how this haltea was moved. So, it is being pushed down and the force changing here. So, you can see clearly the output of the compliant mechanism changing the image processing. This interface will show you. Okay. So, this was used there, and lot of different samples, dehydrated, live samples, hydrated. So, some insects were I guess used in this study. So, many insects as you can see, and the linearity of the movement that is calculated with the force, angular deflection calculated from the displacement, they were able to get the torsional stiffness that they wanted. So, this can be used by others, this sensor, because principle is straightforward. Now, later on all these are former students from our group, Shantanu Chakrabarti, Ramnath Babu and Santosh Bhargav. They extended to dual range force sensor. Just like we had dual accelerometer, dual axis accelerometer, here dual axis in plane force sensor. So, when you are moving something, the force can come in two orthogonal directions. So, they made using a compliant mechanism. They also found out why is it needed dual, you can use two sensors this direction, and also to have different ranges. So, they took another one here, that range can be changed with a little adjustment of the mechanism. They also got motivated with Gecko, which uses the nanostructured surfaces to hold on to the vertical walls and go there, basically adhesive force that is there. So, this paper wanted a force sensor that whose range can be adjusted, range not sensitivity resolution. So, they took that thing and gotten two lengths of the beams. When you fix it here, you get one range, when you fix it here you get another range. So, they made an adjustable compliant mechanism where the output displacement can be varied. So, either you leave it open, then the fixing here makes sense, when apply some force here it will move by something. Now, when you fix this and fix this, the beam length has changed, beam stiffness has changed, the entire compliant mechanism has changed, then it can take larger force over a larger range, but sensitivity will be affected. That is what they have done. Again, in this work also kineto elastic maps were used to decide the size of it, and the dimensions were determined based on that, and some more adjustment had to be done for selecting this suspension for these things, so that in plane it will not move in ways that you do not want to have it move. And they put this over here, the little suspension as I call it, either fix it here or fix it here, and they are able to enable the dual range and dual axis with low cross axis sensitivity. That is, when there is F force and Y force, you have to really decouple them. So, let us say there is only X force, Y may still show some reading, and that reading should be very small, that should be discounted as noise, and beyond that you have resolution for Y axis or X axis, you can tell how much is the smallest change that you can determine. So, they had for both fixing here versus fixing here, they generated these maps, arranged this for symmetry and made this in multiple layers. So, this device, and there was this probe which are attached. This is the one that will touch something, where it will give you X force and Y force separately, and this is how it looks. It is all still solid model, and this is the real device that you see there, and there was a load cell for calibration here. This is not micronewton here, it is more millinewton. There is a load cell to calibrate this, and this is quite non-linear, but with effort it can be made linear also. This is displacement versus force, and this is a graphical user interface like the last one, and I guess there is a movie to see how this dual range dual axis thing works with compliant mechanisms with adjustability. So, these are all the solid models as to how it looks and how it was composed and how it is assembled, different layers, and the final one, this is the probe, which is what can move x and y, and all the pose and everything, adjustment of these pins. So, you can change the range of the accelerometer, that was that. This is the prototype. You can see it is big and it can measure very small forces. The in plane forces, the horizontal and two directions in the plane. Okay. So, the main points of this is that we can actually make a practical or practicable packaged micronewton force sensor using compliant mechanism. There is nothing here other than the little microscope, and it is slow, 10 to 100 hertz is that limitation, but with some more design we can make it at high speeds also, but the speed is limited by the microscope, not the mechanism here. Mechanism can be made to have higher resonance frequency, but your frames per second will decide how fast force changing can be detected with this sensor. It can be calibrated, tested, single axis as well as dual axis. One can also extend it to 3 axis also. Nanonewton levels are also possible, but it all depends on your microscope capability in resolving displacement, and of course compliant mechanism is the one that is going to amplify the displacement over here. Okay, thank you.